Okay, so again, here's the Lorentz transform equations, and I want you to notice how symmetric they are when they're written in this form. So Ct prime is equal to gamma times Ct minus gamma beta times x, and x prime is equal to minus gamma beta times Ct plus gamma times x. So you can see that if we write it such that the Ct terms are first and the x terms are second, then you get gamma minus gamma beta minus gamma beta gamma. Okay, so this symmetry is actually even more apparent when we write the Lorentz transform equations in matrix form. Okay. Okay, so here are the Lorentz transform equations written in matrix form, and recall that when you multiply a column vector, in this case a 4 vector, four coordinates, the time and the three spatial coordinates, by a matrix, the way that you do this is that you take each element in the column vector gets multiplied by a particular row. So it would be gamma. So Ct prime is equal to gamma times Ct plus negative gamma beta times x plus 0 times y plus 0 times z, which is exactly this equation here. And similarly, x prime is equal to the second row times the column vector. So it's minus gamma beta times Ct plus gamma times x plus 0 times y plus 0 times z, which gives the second row, second equation. And similarly, y prime is equal to 0 times Ct, 0 times x, 1 times y, plus 1 times z, and so on. Okay, so you need to review your matrix algebra if you've totally forgotten this. But basically, to get a column vector from another column vector, we multiply by a matrix where the elements of the column vector are multiplied by each row to get each successive element in the product column vector. Okay, so that's and here you can see you can really notice the symmetry. So if you look here in this little part here, this corresponds to the two most important equations, the first two equations, and you can see the total symmetry in this submatrix there. Okay, now let's move on to velocity transformation. So we've shown you how to transform using the Lorentz transforms, the Lorentz transformation. You can go from one coordinate system to another, one reference frame to another. You can transform the coordinate values, the time coordinate and the spatial coordinates. Now we want to find out if something's moving besides the two reference frames. One reference frame is moving to the other, but if there's objects moving in these reference frames, how do we transform their velocities? Okay, so recall that in classical Galilean transformations, okay, velocities just add up in a very simple way. For example, if we have two reference frames s and s prime, where again s prime is moving with velocity v to the right, and if there's a person that's at rest in s prime, so maybe s prime is a spaceship moving, and that person throws an object, a ball, to the right with velocity u, right? Then in the classical Galilean transformation, right? So we have ux prime is equal to u, and uy prime is equal to uz prime is equal to 0. So it's just moving to the right. Okay. So in a classical Galilean transformation, a person in frame S, that's a person in frame S sees that the velocity of the object is equal to v plus u. The velocity to the right is v plus u, and again uy is equal to uz is equal to 0. Okay, and so I want to emphasize that this is wrong. Okay, in general this is wrong. It's very accurate. It's a very good approximation when you're working at non-relativistic speeds. That is, when the two observers are moving with respect to each other very slowly compared to the speed of light, then this velocity addition rule